Hi viewers, today promises to be an interesting one as we move into the second part of the trigonometrical ratio. Today we shall be treating Pythagoras Theorem and solving other advanced questions from trigonometrical ratio. Olarewaju Bolaniwa is still my name. Teaching is my calling. So let's start with today's business. Pythagoras Theorem. So when do we use Pythagoras Theorem? We use Pythagoras Theorem when we are given a right angle triangle and we are looking for a side from the right angle triangle. An illustration is this. Let's assume that we have a right angle triangle like this. This is where the right angle is facing. So of course this is going to be our hypotenuse. And let's assume that this place is given to be 5. Assumption that this place is given to be 6. So we are meant to find this side of the right angle triangle. This is when we can apply the Pythagoras theorem. So to apply the Pythagoras theorem, we need to learn how is the formula like. For Pythagoras theorem to be applied, we need to have our hypotenuse, which we are going to say hypotenuse square equal to opposite square, then plus adjacent square. As we have done in the earlier video, we have seen where the hypotenuse is wherever the right angle faces. And for the two sides, it depends on the angle at which you are looking at it from. But in this case, no angle is given. So we don't really need to identify a place as the opposite or the adjacent. So far we are adding the two together. And it's very possible too, in an assumption, maybe this is where we are looking for, and they've given us the hypotenuse to be whatever, maybe something like 9. So to solve this, we are still going to use the Pythagoras theorem, which states hypotenuse square equal to opposite square plus adjacent square. So in a nutshell, Pythagoras theorem states that hypotenuse square is equal to the two sides, of which we are going to square the two sides and sum them together. So let's see how it works from a given example that we are going to see in the next content. Without further ado, let's see what we are going to get out of these questions by applying the Pythagoras theorem. A right angle triangle is given, of which it is partitioned from here, stating that from here to here is x, and from here to here is y. Of course, it's a right angle triangle, but we can look at it in two ways. Looking at it from this place to this point and to this point, x happens to be the hypotenuse. And also assuming that from here down to this point and to this point, y happens to be the hypotenuse. So let's start from the inner part of the right angle triangle. Because before you can apply Pythagoras theorem, two sides must be given before we can get the third side. Meaning that if we choose to start from here to here and to here, of course it will equally work, because from here to here is going to result to 9. But I choose to start from finding x first. So let's see what we have for the A. Considering this right angle triangle, I'll quickly itemize it here. This is of course my hypotenuse, which is x. And I have from here to here to be 12. From this point to this point is going to be 5. So I have it as 5. As Pythagoras theorem states, hypotenuse square equals to opposite square plus adjacent square. So this gives me x square equal to 5 square plus 12 square. Like I said earlier, we don't need to bother which one is opposite, which one is adjacent, since we are adding them together. So we proceed by having x square equal to 5 raised to power 2 will give us 25 plus 12 raised to power 2, we have 144. Then x square is going to be equal to the addition of these two, which will give us 9, 6, and 1. So by the time we find x is going to result to the square root of 1 169. And the square root of 169 is going to give us 13. We have 13. Then to move to the next one, which is the bigger right angle triangle. So we are going to draw it. I choose to draw it again. This time around, the base of the right angle triangle is going to be 9. Because from here to here was what we used earlier. Now, in order to solve for y, we have to assume that these whole base are coming together to be 1. So we have it to be 9. For the base, we have 9. And for this, for the height of the right angle triangle, we have it as 12. Of course, we are looking for y again. So that results to having y squared equal to 9 squared, then plus 12 squared. So y squared is going to give us 9 raised to power 2, we have 81, plus 12 squared again, we have 144. Y squared is going to give us, this is going to be 5, and we have this to be 12, we have 1, then we put it here, we have 225. Then finally, to get our y, is going to result in the square root of 225. So y is going to end up to be 15. Easy. We have this b. It's quite an interesting one for this b. All we need to do is to apply our idea from plane shapes. We have a rectangle here. Attached to it is a right angle triangle. From here to here is 13. From this point to this point, which is y, then we have from this point down to here to be x. So we are meant to find x and y. Starting with the first concept, since here to here is 24 and they are parallel to each other, definitely this place is also going to be 24. Upon having that place as 24, the next thing is to identify what this place to this place is going to be. If you look at it logically, these points or this side and this side, they are equally parallel to each other. That means if this is 6, definitely this place is also going to be 6 from here down to here. It's also going to be 6. Upon having it to be 6, now what will be this point from here down to this place? All we need to do here is to remove 6 from the whole of 13. And by the time we do that, it means from here to here is going to be 7. X is going to be 7. Easy. So let's just get it written out. Since from here to here is 13, and we have from here to here to be 6. So by the time we remove 6 from the 13, it will give us the remaining part of this distance from here to here, which means 13 minus 6 will give us 7. Now we have our x to be equal to 7. Now the next thing is to identify what our y will be. This gives us a right angle triangle looking like this. Of course, we have found our x to be equal to 7. We identify that from here to here is 24. And finally, we have our hypotenuse, y, which we are looking for. So, to solve for that, we are going to have y squared equal to 24 squared plus 7 squared. Y squared is equal to, let me punch that, 24 raised to the power of 2. So we have 576 plus 7 raised to the power 2, we have 49. So y squared is equal to the addition of the 2 plus 49. This leaves us with 625. So y is going to be equal to the square root of 625. So the square root of 625, y is going to be equal to 25. Easy. Wow. I'm loving this. We have this amazing shape here, a rectangle, where we have the side to be A, E, B, C, and D. Inside of it, we have a triangle on it, stating that this side and this side are equal. So it's an isosceles triangle placed inside of the rectangle. Now we are asked to find AE from this distance A down to E. Equally find EB from this E down to this side. And finally, EC from this E down to this C. Now let's see how we're going to start. To start with, since I said earlier that this indicates that it's an isosceles triangle, whatever the distance is from here to here, it's also going to be the distance from here to here. This leads us to, as this place is 5 centimeters, definitely this place is equally 5 centimeters. So we have the 5 centimeter here. Upon having this, we now see, obviously, that a right angle triangle is given here, and we are asked to find the AE. To get the AE, we bring out this triangle. We have for A, this triangle, like from this AED, from triangle AED, this is my A, I got E here, and the D is given here. Of course, this line is this line, which is 5 centimeters. Then, from A to D is given to be 4 centimeters. Now, I'm looking for AE. Using Pythagoras Theorem, this is the hypotenuse. We have 5 square to be equal to 4 square. Now, plus AE. Let's add it to be AE square. So, 5 raised to power 2, we have 25. 4 raised to power 2, 16, plus AE raised to power 2. Of course, we make AE subject of the formula. So we have 16 travels to this side, the sign changes. We have 25 minus 16 equal to AE raised to power 2. So by the time you remove 16 from 25, you are left with 9. So that gives us AE raised to power 2. So by the time you look for AE without the square, that means square root both sides. We are going to have the root 9. So AE is going to be 3 centimeters. Easy. Having done that, let's see how we get our EB. Since we have identified the AE to be 3 centimeters, so we have 3 centimeters here given. And from here, from D to C is 5 centimeters. If from here to here is 5 centimeters, so by the time we remove this 3 from the whole of the 5, we are going to have EB to be equal to 2 centimeters. Easy. We have 2 centimeters here. So to solve that, we can say since CD or DC is equal to 5 centimeters, that means EB is going to be equal to the A to B, which is also 5 centimeters. We are now going to say the 5 centimeters minus the AE, which we have just identified, which we have just found from this, which is 3 centimeters. It will leave us with 2 centimeters. Easy. Now let's move to the C. To get the C, which is EC, this distance, we have been given the distance A to D to be 4 centimeters. So this is equally 4 centimeters. Having done that, we can identify that we have another right angle triangle, which I'm going to draw here. We have this, which is the EB. we have the E, and we have the B here. Then from the B down to C, then we have from E to C. E coming down to C. From B to C, we have it to be 4 centimeters. Then from E to B, we have it to be 2 centimeters. Now we are trying to find the EC. This is the hypotenuse, of course. So the EC square is equal to the BC square, which is 4 square, plus the EB, which is 2 raised to power 2. So we are looking for the EC, of course, equal to 4 raised to power 2 will give us 16, then plus 2 raised to power 2, we have 4. Then EC raised to power 2 is equal to 20. Looking for the EC is going to give us the square root of 20. So if we choose to leave it in such form, it's going to be EC equal to 4 multiplied by 5. Then this gives us the square root of 4 is 2. We have 2 root 5 in centimeters. And if we choose to leave it as decimal, all we need to do is to punch the calculator. The square root of 20 is going to give us 4 point something. Easy. Yes, here comes another twister. We are given that if tan theta is 8 over 15. Now, find the value of what we have here. Sine theta plus cos theta. Everything all over cos theta, open bracket, 1 minus cos theta. Easy is how it's going to be. Now, let's start. Of course, given that tan theta is 8 over 15, it indicates that, let's assume we have a right angle triangle like this. Having a right angle triangle like this means the theta, you can place it wherever we choose, the theta here. Tan is always opposite over adjacent, TOA, based on what we have done earlier in the beginner's level of trigonometry. So tan theta means we are going to have opposite over adjacent. Of course, this is the hypotenuse. Opposite, tan theta, opposite, 8. We have 8 here, over adjacent, we have 15 here. Now we can apply Pythagoras Theorem to get the hypotenuse here. In order to get that, we can say the hypotenuse square is equal to 8 square plus 15 square. The hypotenuse square is going to be 8 raised to power 2, we have 64, then plus 15 raised to power 2, which will give us 225. The hypotenuse, without wasting time, is going to be the square root of the addition of the two. So we are going to have 9, then we have 8, then 2. The hypotenuse to be equal to 17. We have this place to be equivalent to 17. Now we have the 3 sides. We now proceed to what we are given here. Like, what is it going to generate for us? Sine theta. Sine is so. From this right angle triangle here now, sine theta is going to be opposite over hypotenuse. That means it's going to be 8 over 17. We equally have cos theta. Cos theta, that is adjacent over hypotenuse. Cos, this is adjacent over hypotenuse. That's 15 over 17. What else do we have? We have cos already and another cos. Fine. All we now need to do here is to substitute these values into the expression we have here. Sin theta is 8 over 17 plus cos theta, which is 15 over 17. Everything divided by cos theta. Cos theta is 15 over 17 multiplied by 1 minus cos theta. Cos theta is 15 all over 17. From here, all we need to do is to simplify what we have here. Then we get our answer. Easy. We have the denominator to be the same. Of course, for the numerator, all we need to do here is, of course, it's going to be over 17. So we have 8 plus 15. So by the time we add 8 and 15 together, it's going to give us 23. That's for the whole of the numerator. Now, for the denominator, but before we go to that, this is a division sign. So I can decide to spread it like this, like, okay, divided by. Now, back to what we have here. Let's decide that we want to leave this 15 here to start with. We have 15 all over 17. Then multiply by, this is 1 over 1, whatever way, or we multiply the 2 by 17. So if you choose to work it like this, no problem with that. So we have 17. So 17 divided by 1, we have 17. 17 multiplied by 1, we equally have 17. Furthermore, 17 divided by 17, we have 1. Then 1 multiplied by 15, we have minus 15. Close bracket. We move to the next level. 23 all over 17 divided by 15 over 17. This value. Then it's getting clearer. 17 minus 15. We have 2 all over 17. Close bracket. Without wasting much of our time, we now cut. But it cannot work that way. We cannot cut in this case. All we need to do here is 15 multiplied by 2. So we have 23 all over 17. Still divided by 15 multiplied by 2. We have 30. Then we have 17 multiplied by 17. In order not to make any mistake, we have 289. Now we make use of change in form. We change the form. This division we turn to multiplication. In that case, the 289 will take the position of the numerator, and the numerator will take the position of the denominator. So we have 23 over 17 multiplied by 289 divided by 30. 17 goes here, takwa. 17 goes here, takwa. We have 17 again. So we are left with 23. 23 cannot go in 30. So let's try to multiply 23 and 17 together. So 17 multiplied by 23. This will give us 391. All over, we now have the denominator to be 30. From here, nothing can go in the 2 from what we have here. So let's just divide it by 30 to give us, we are left with 13.0333 and many tricks. So rounding this one up to the nearest whole number will leave us with 13. Easy. Yes, apart from taking the task, if you have received value for this video piece, please kindly press on the subscribe button, share with your friends and colleagues, and ultimately keep liking this video, and your answers, place them in the comment section below. I can't wait to see you the next time, where we shall be visiting the advanced level of the trigonometrical ratio. Until then, have a wonderful time.